Good morning. Thank you for coming. I'm just going to jump right in because we're on limited time. So I'll start by just telling you a little bit about who I am and what the talk is going to be about, what sort of things we're going to cover. My name's Ryan. I am by day the Director of Decision Engineering at Grubhub. My group works on things like automated dispatch algorithms, courier scheduling, simulation, that sorts of things. We are a sister group to the data science team as well. So my background is in computer science and operations research. Can I get a show of hands of who out there actually knows what operations research is? It's a fair amount, okay. If you don't know what it is, you're not alone. It is probably the worst named field in pretty much all the quantitative disciplines. It was formed out of the World War II military-industrial complex when we realized collectively that we could take human systems like factories or transportation networks or grocery stores, anything like that, and model them mathematically and improve them using optimization and mathematical techniques. You may have heard the saying that data science is the sexiest field of the 21st century. Operations research is sort of the sexiest field of the 1950s. Lately, there's been some interest from the data science community in learning about optimization and operations research techniques. So this talk seeks to take the grounding that you have as data scientists and build optimization understanding around some of the models that you already understand. And that's a good starting point because under a lot of the sort of classical inferential statistical techniques, especially things like regression, there's always an optimizer somewhere in there. So we can take something like a least squares regression, we can model it using scikit-learn, we can then deconstruct it a little bit and say this is how we treat it as an optimization problem. And then from there, we can build more general models that do other things and like make decisions. And the reason for this is that you want to do this is that the more general or abstract optimization techniques go sort of a step beyond some of the things that you can do with predictive models in that they handle interactions between complex decisions well. So we'll spend a lot of time on formulation. There won't be a whole lot of math. There will be a little bit. I'm not a statistician and I'm not a mathematician, so if you see an error, let me know. It'll improve the slides and maybe I'll buy you a beer. But there will be a lot of different kinds of models that we show. I think I'm going to give 3 data science models and a couple application type models that we build off of those. You can follow along, by the way, with the IPython notebook. It's in my GitHub, Ryan J. O'Neill, under the talks repo. Just look for the current date if you're that sort of person. There's a requirements.txt, so you should be able to run everything. Just make sure you're using Python 3, because Python 3 or go home. So we'll go a little quickly, but the key takeaways here are that many of the statistical inferential techniques that you're using already have optimization under the covers. If you want, you can take an optimizer, you can model them the same way. Maybe it won't perform quite as well as what you're using in scikit-learn because it's not specific to that purpose, but it's a great way to understand how optimization works and how you can take those same technologies and do more general models with them. So as with any sort of statistical inference work, we start with least squares. So basic problem statement, we observe some noisy data. We want to fit a curve to it. So noisy observations, infer a function. We're going to generate some random data to start with. This way we have a ground truth to compare to. So I'm just going to use the function y equals 3x squared minus 2x plus 10 plus epsilon, where epsilon is a Gaussian random variable. So that's my noise right there. I'm just going to plot a curve and add noise to every point on it. So here's a little code to do that. You can see I'm just generating random data here. The yi section, yi equals section, is the function that we talked about. And the eps, which we add to it, is just the noise parameter. I'm going to stick these in NumPy arrays. I apologize for the code in the IPython notebook. I tell people that I write old man Python. None of the fancy tools like pandas. All right, so we plot this. We get a nice curve, a little bit of noise in there. So now we have a ground truth and we have some random data that we've generated that we would like to fit and see if it compares favorably with our known ground truth. So first way we'll do it is with scikit-learn. Right? So this is pretty simple. All we have to do is import the regression class in scikit-learn. I'm not going to go into determining what the features are, but assuming we've done our homework, we've looked at this curve. We've said, gosh, it's got a nice upwards curvature. There's probably a linear component to it and maybe an offset, so I need to fit it to those three pieces. Right, so we want a quadratic term, a linear term, and an offset. So this is your basic scikit-learn linear regression model. All I got to do is import linear regression. I'm going to manually construct my feature matrix. And you can see here, I'm explicitly giving it the 1 for the offset because I want it to come back. I want it to fit the model that way because I'm going to do that again later, right? So I've got my squares, my squared terms, my linear terms, and my offset terms. So I construct my feature matrix X manually this way. I just fit that to the observed data. And it gives me back 3, -2, and 10 approximately, which is what I put into it. So that's good. Okay. How'd we do? Well, that looks about right. Okay, so next. We're not going to do this with the other models, but with linear regression, or least squares, it's so convenient, we might as well. If we didn't have a computer, what we would do is we would think about the function that we want to minimize. Right? So in least squares, what I want to minimize is the sum of the squared residuals. So y is my observations, and x beta are going to be my predicted values. So y minus x beta is the residuals. Right? I square these, they all become positive, and I just sum them up. And so now what I have is a function that defines a function that I would like to minimize. What I want is to find values for beta that minimize the total value of that function, right? And you'll notice here that I've just added a 1/2 to the front of it. That's simply for the convenience of the optimization. It doesn't really matter if I'm minimizing this function times 1/2 or times 1 or times 2. As you get into different kinds of optimization for regression, there's different norms you can use as well. And so one of the things that's convenient or cool about using an optimizer to do things like regression is that it becomes very easy to switch out different norms. A lot of the time we use least squares regression because it's really convenient to work with it because of the nice closed form solution we get out of this. So if I just multiply my terms through, I end up with this function at the very bottom, which is 1/2 y transpose y, so on and so forth. This is the actual function of my residuals, right? This is the sum of the squared residuals. So if I can find a minimum for this, and it's nice and convex and all that other good stuff, then I have values for beta. So I dig out my calculus book, and what we do is we take the first order derivative of this function and set it equal to 0, and I know that'll be a stationary point, right? And since the function is nice and convex, it'll also be the global optimum. Solve it through, and I get this beta equals x transpose x inverse x transpose y, which is the pseudo-inverse. So what have we done here? What we've done is taken a problem that it's kind of hard to solve because we've got lots of observations which form these equations which conflict with each other. And we have now reformulated the problem as a minimization of error. So this restructuring of the problem allows us now to solve it. We'll get a little bit more into that later. But basically what we've done is taken something that is unsolvable and reformed it into something that we can solve. And now we've used optimization to solve that new thing. Yes?
We found it hard to imply the reform that has the slide.
Look for Ryan J. O'Neill on GitHub, and there should be talks, and then under 2017 July.
Okay, thanks.
Mm-hmm. And you'll have to use the requirements.txt in there if you want to, because it requires some libraries. So let's implement this using NumPy directly. So this is just where we're going to do beta equals that pseudo-inverse function, and then just print out the results that we get. And you can see they're the same as what we get. I believe they're exactly the same as what we get from scikit-learn. Let me check that. 3.01. Negative 2.10. Yeah. So it gives us the same result. Yes?
Do you have a time result?
I didn't time these. They're both so fast you wouldn't even notice. If you were really doing this, not just in a toy problem, you wouldn't do an inv on this because that's inefficient. You'd probably do some sort of factorization, Cholesky decomposition, or something like that. And I'm sure that's what scikit-learn is using internally. I actually have no idea. But yeah, with these kinds of problems, you can think of these things as just technologies. They're so fast and they are numerically stable that generally you're just going to put information into them. It'll just come back to you with a good solution, almost all the time. All right, so how'd Grandma and Grandpa do with their chalk and slab of slate and NumPy? Same solution. So that's all well and good. But we've gone from feeding this data into scikit-learn and having it do all the heavy lifting for us now to thinking of it with an analytical or closed-form solution. Let's do it a different way. So let's say you have this crazy Uncle Eddie that used to do optimization back at NASA or something like that. When he thinks about least squares, what he thinks about is there a more general technique that I can solve problems with this like this with? And he knows that in the CVX opt package, there's a QP method for quadratic programming, ignore the term programming, that can solve anything of this form, right? So it can minimize anything where P, I believe, is positive semi-definite. And it's more general than the form we just used to solve least squares, right? So if you ignore the subject to the constraints at the bottom, this top function, this minimization, looks pretty familiar, right? i.e. it looks a lot like this. If we just rearrange the terms and we drop out that 1/2 y transpose y, which is a constant, so it doesn't even matter. Right? So if we're going to solve it with this, all we have to do is reframe our objective function and fit it into this model, and our solver will do the heavy lifting for us, right? So how do we do that? So we have to convert from this form. Here I've rearranged the terms. And all we have to do is say P equals x transpose x and Q equals negative y transpose x. And now I can stick it right into that solver and it'll just do it for me. Okay, so this is the third way of solving least squares. And again, the 1/2 y transpose y is a constant, so we just drop it. P, I believe, has to be, if you look at the CVX opt docs, I think it says that it has to be positive semi-definite, but that's going to be the case with x transpose x anyway, so that's fine. So here is the CVX opt version using QP. I have to do a little bit of munging to get the data into the right format, but as you can see, it gives me back basically the same solution that least squares did. And you should expect, I think, generally with this, it will be fast, not quite as fast as your scikit-learn least squares solver, because this is using, I think under the covers, probably an interior point method or something like that. It is using a different solution technique, which is more general and solves classes of problems. So here's the output of Uncle Eddie's version of least squares. So we can see it's the same. So we've now just solved least squares 3 totally different ways. We've solved it using scikit-learn, sort of an out-of-the-box approach. We've solved it using a closed-form method, the hard way. And we've now solved it using an optimization solver that can solve anything that's a quadratic program. So any problem that meets these criteria, it can solve. So why would we go with this third technique? What does it give us? The real advantage here is that in decision modeling, what we try to do is create algorithms that solve general classes of problems. And then when we need to solve a problem, we identify what class it belongs to and we model it using that, right? So the problems themselves are somewhat separated from the algorithms that solve them. And so there's the activity of algorithm development and optimization, and there's the activity of model formulation. And that allows us to think about things very separately, but it also allows us to apply very specialized tools to large classes of problems. So if you think about, well, I want to use least squares to solve a problem, but I want to make a small modification to it. How would you do that? Right? If it's not something that's supported by scikit-learn or a similar tool, that becomes very difficult. But if you've modeled it using something like a quadratic optimization solver, well, now I can throw in different kinds of regularization. I can make it epsilon insensitive so that, if I know I've got a certain kind of measurement error that I'm dealing with, I can just ignore it. Or a lot of other things that my optimization solver will allow me to do because it solves a more general kind of model. All right, so let's go through an application. This is going to take that same quadratic optimization solver, and it's going to do portfolio optimization with it. So it's going to use the same exact code that we used to solve least squares in the third instance, and it's going to now optimize a portfolio. All right, so the basic idea with portfolio optimization is we have a bunch of money. We want to put it into different investments. And those investments have expected returns, and they have covariance matrices on their returns. And so we want to maximize our returns such that we minimize the risk that we're subject to, right? And so our inputs to this model are the amount of money that we have and the different investments we can put it in. Of course, we can't make negative investments in this model. And our risk tolerance, which is sort of this unitless measure. We're going to take 100 months of exchange rate data from the Fed. I just have this sitting around from 2014, so we'll use that because it's convenient. If you want, the link in the slide in the IPython notebook actually will link directly to the CSV, so you can solve this yourself. Although I haven't updated this particular data set in a few years. All right, so this is what our optimization model looks like. Mu is the vector of expected investment returns, just based on historical data. So of course we're making the assumption that the past will look like, or the future will look like the past. I guess the past would also look like the future in that case. We'll compute a covariance matrix. This will help us minimize our risk. And alpha is our unitless measure of risk aversion. And what we're going to do is we're going to fiddle with alpha, and we're going to generate a Pareto front, which allows us to make trade-offs between risk and return. So the model itself is pretty simple. We're going to maximize our return minus alpha times our risk, right? So mu x, that's our expected return. Alpha x, sigma x, that is the measure of portfolio risk. That looks similar to the model we just solved with least squares. And then we're going to do the sum of all our investments has to be 1, right? So they're non-negative. I can't make a negative investment. And if I invest 0.1 in some particular currency, that means I'm investing 10% of my assets in that currency. So they have to sum to 1. All right, well, this is a maximization problem, and we just solved a minimization. So how do we do that? We just multiply by -1, and now it's a minimization problem. So this is our model. All right, we covered this. So we're doing, obviously, a convex combination of the investments. All right, so we pull everything into pandas. I lied when I said I didn't use pandas. Compute our covariance matrix. And now we feed it into CVXOpt. We're feeding it into the same function. This is still the QP function. We have a lot more arguments to it. because we have those constraints on it now. Essentially, we have the constraints that the investments are non-negative and that the sum of the investments has to equal 1. So we're investing our entire portfolio. But it's the same function. And now what we're going to do is we're going to run this against lots of different values for alpha. And you'll get a lot of awful looking output. And you'll get a curve looking like this. So what we've done here is taken a very generic method for solving quadratic optimization problems, and we've applied it to 2 completely different things. In one model, our decisions were, what are the values for beta? How do we fit this curve? Are the decisions that we're making. In the second model, the decisions that we're making are, how much of my investment portfolio do I put in this particular asset? Same optimization procedure. All right, let's go to a different model. Support vector machines. So we have 2 sets of points, and we want to draw a separating hyperplane between them. Again, we're just going to generate a bunch of random data and put a line through it to the extent that we can. So we have these epsilon parameters that are just noise, right? So here's some code, generates random data for me. And what we're going to do is represent these points such that we're trying to separate the blues from the oranges. And of course, we can't quite do that because they overlap in the regions. But we can draw a line that minimizes the error. And that will be our support vector machine. So if we do this with scikit-learn, again, fairly simple. We just import the SVM library, and we run fit on it. I'm using the linear kernel here because the use of different kernels is sort of beyond the scope of this talk, but we could use different ones. And what we're looking for here, i.e. the decisions that we want to make, are what are the values that give us this separating hyperplane that minimizes the classification error. And so this is the output of scikit-learn's SVM library in doing that. And the way the classification works is if the value of the observation in that function, in that line, is greater than or equal to 0, then it's of one type, and if it's less than 0, it's the other type. Right. So this is our confusion matrix. So the correct predictions are on the diagonal, and the incorrect ones are the other points. This is just some code, boilerplate code, to get a nice visualization of this going in Bokeh. And this is what it looks like. What I've done here is remove the orange and blue, and the correct ones are light gray, whereas the incorrect predictions are these red squares. All right. So this is our baseline now. All right. So let's try this using an optimization solver. So we're going to use a library called Pulp here. Pulp is a modeling tool that lets us solve anything that's linear, and it can also let us do some mixed integer optimization. So what we're going to do is frame our our support vector machine model such that Pulp can solve it, right? So we're going to minimize these errors subject to a linear set of equations. So how do we do this? Well, we first construct vectors of the inputs for our observations, where xi is the point of the observation, where is it on that graph, and yi is +1 or -1, depending on what kind of thing it is. And then we build a model out of that, where we have these epsilon variables, or psi variables, sorry, that are the actual errors, right? So if a thing is misclassified, then we penalize, right? And these two inequalities here force a penalization onto the linear solver whenever something is misclassified. And you can see with a little bit of algebraic manipulation, those just work down to one inequality, which is kind of nice. So this is the model. This is linear support vector machines. This is one of the models you can use to solve it. So we run this through Pulp, Oh, wait. Yeah. If you think back a few slides, the linear optimization solver solved things that are of the form ax equals b. These are, of course, ax is greater than or equal to b, so we just have to add an extra variable. Transformations like that are fairly standard in linear optimization. And so this is just getting it into the right form that the linear optimizer can understand. All right, so let's create a pulp model. So these are our decision variables, B, W1, and W2. We also create variables for our errors, though those aren't exactly decision variables. These are variables that we are going to optimize against. So we're going to relate the error variables to the decision variables and penalize based on the errors. So this is that nasty looking constraint that we saw earlier. We just add it for every observation. And we set an objective function being the sum of those errors, and we solve it. I'm going to create a predict function. Of course, normally you just do this with scikit-learn directly, but since we're building everything ourselves, this just determines whether it's a +1 or a -1. And we get the same confusion matrix. So that's all well and good. So now we've just built our own support vector machine. I'm going to skip by the problem shapes because we are running low on time, but it's kind of interesting to think about if you go through the slides. Okay, third model that we'll cover is clustering. So let's say we have a set of unclassified data and we want to figure out how to cluster it together around centroids. All right, we'll generate some data just like before. So again, random data with noise on it. So these are our centers. I'm just going to choose them a priori. We're going to have 3 clusters. All right. So this is what it looks like. All right, we'll do this with scikit-learn. So again, I import k-means here. I fit it. It's nice and fast. It does a good job. And it gives me these as my centers, which are roughly right-ish, close enough. And I'm going to build a plotting function that just shows them by color and shows me where the centroids, where the model decides the centroids are. So gray here are the model centroids, or cluster centroids, and then they're done grouped by color. Let's do this with linear optimization. In this one, we're going to have to add variables, binary variables, to determine which centroid, which cluster a particular observation goes with. And we'll have linear variables that penalize its deviation from its assigned centroid. Right. So we have a new set of variables y, which are 0 and 1. And this actually makes solving our models, it can make them a lot harder. And in this one, it will. And it's just simply because it's not continuous. Right. So you have to employ different methods. But I'm still using the same optimization solver or optimization library to solve it. All right, so our inputs, locations of the observed points. And we have to make 2 kinds of decisions here. One decision is, where are the centers? Where do I put my centroids? And the second decision is, which cluster is each observed point assigned to? Since it's a linear optimizer, I'm not going to be using Euclidean distance. We're instead using L1 norms here. So this is a representation of that. And this is what the model looks like. So primary decision variables, locations of the cluster centers. Secondary decision variables, which cluster do I associate each point with? And we require that each point be associated with exactly one cluster. Fairly simple. This just guides the optimization using the L1 norms or the taxicab distance. And we're not going to talk about symmetry elimination. And then we set our objective as the sum of the distances. So again, we're optimizing over something that is related to the decisions that we're making. Running it actually takes a while for this model. There are better models for clustering and integer programming. I'm not going to talk about those here. And so again, we create our own predict method and get out a similar result. It's put the cluster centers in a different place. I'm assuming that's just because we're using the taxicab distances. But hey, we just built our own clustering system. That's kind of cool. So the problem here is that if you run this model, it'll probably take a minute or so to solve even a very small set of data, right? There are much better ways of doing this in integer programming. They're way beyond the scope of this talk, but I'd like to show something that is a little more realistic with the minutes that we have left. So our second application is going to be pedicab sharing. I created the slides before all hell broke loose. So, you know, your brother and your grandmother and your parents have all started ride-sharing companies, so you decide that it's your turn. So what we're going to do is generate some pedicab locations, and we're going to say that each pedicab can have up to 2 people at a time. And then we've got a bunch of people that we've got to pick up and drop off, right? So this is essentially what's called the dial-a-ride problem, if you look in the literature. Right? So this is just a function to build out where the pedicabs are and plot them. And what we see is, this is just random data again, but the green squares are the pedicab locations, blue triangles are pickups, and their drop-offs have dotted lines to them. So this is the demand that we have on our system right now. So our questions really are, what are the routes that we give to these pedicabs, and what pedicab picks up and drops off which customer? So we'll use a technique called column generation. All of these examples, by the way, are just sort of textbooks, so there's references at the end. You can find them all in there. I did the service of translating it all into Python for you. So column generation is we're going to generate a bunch of routes, and we're going to use an optimization to determine which of those routes to use. So we're going to generate a lot of routes, a lot more routes than we actually need. And then the question is, which is the set of routes that will serve all our customers at the minimum cost? And then we're going to subject it to a model that is a partitioning model on one side and sort of a packing on the other, i.e. we're going to service every customer, and every pedicab can have no more than one route. So we've got these we're going to cover and pack basically at the same time, depending on how you think about it. All right. So what we're going to do is run a little code that generates a bunch of different routes for our pedicabs, all the feasible ones, and score them by distance. And that's what this code does. And we have, at the end of that process, 2,387 total possible routes to choose from. We have a binary variable with each route deciding whether or not to use it. And each customer gets serviced by somebody, and no pedicab has more than one route. We just add constraints for that. Now our objective is to minimize the total distance. And we'll think of that as a proxy for cost to us. In reality, we probably have something very different. And our total cost ends up being 814. So we plot our solutions, and that's what it looks like. And then the pedicabs come back to us and they say, well, I have to travel too far, right? So now what we're going to do is we're going to add a secondary objective, which minimizes the total, minimizes the maximum trip length, right? And so that makes our costs go way up, but their route lengths go way down. Well, that's not very good for us, right? So now what we do is solve another optimization problem, which says, well, give the pedicabs better routes or shorter routes, but only hurt our margins by 10%, right? And so now we can see that we're closer to our original cost, our best cost, and our routes are not as long. And we get this sort of a solution out of that. And so this is a more realistic example. Solves very quickly. So I have some links in the Python notebook as to good books that you can look at if you're interested in this kind of stuff. I also have to give a quick shameless plug for Grubhub. We're looking for data scientists, data people. If you're interested in that kind of stuff, our mission is to use math to feed the hungry. So you can email me or find me here.
Thank you, Ryan. Great session. We'll take a few quick questions.
Thank you. Maybe it's just because I'm too silly. Jupyter cannot open your notebook. It says it's not JSON. So what should I do?
I will make sure that it is working. Yeah, so the question was, what's wrong with the notebook? And I'm not sure at the moment.
Anything else?
Are you sure you're using Python 3 in the appropriate version of Jupyter? I will make sure that it is working. Email me if it doesn't. We have a working one.
All right. Any other questions?
Sorry, you definitely covered this, but can you go back to talking about some of the benefits of these more flexible models over just using the libraries? Because part of it felt like a lot more work for the same results, right?
Yeah, I would say that if your plans are to do statistical inference, you're probably not going to use these. The purpose here was just to use it as a launching pad for getting into more general purpose decision modeling. So if your interests are what capital budgeting decisions do I need to make? How do I need to route my drivers? How do I need to invest my money? That's those sorts of questions. Then these are the kinds of tools that you'd want to use. But for statistical inference, I probably wouldn't. Oftentimes with things like the scikit-learn libraries, they are well adapted to those kinds of problems, and they are custom and much faster. And of course, the question was why would you use this as opposed to something like a scikit-learn?
Last question.
So in machine learning, we use gradient descent very commonly. So what do you think about the use of the gradient descent method in operation optimization?
So I have to confess a little bit of ignorance. I'm assuming you're talking about things like XGBoost. The question is, what about using gradient descent in optimization?
Yeah.
So if you're doing something like convex optimization, and you're just using the gradient, you're going to get a fairly poor optimizer. But that doesn't mean that such methods aren't applicable. In most optimization libraries, we like to have second-order information because that gives us curvature. But it may not always be available. So those methods are also useful. And I don't know much about that, the applications of those in machine learning, but my impression is that those tend to work very well with machine learning libraries, so I wouldn't discourage it. But if you can get second order information on a model, it's always good to do so.
That's all the time we have. Thank you, Ryan. Great presentation.